Okay, in this particular video, we're going to continue in our calculation or our solutions to the problems. We're going to take a look now at the problem in 10.4-7. This is, as we see here on the screen, this is a heat pump that operates on the ideal vapor compression cycle with R134A being our refrigeration, and it is used to transfer heat at the amount of 20 kilowatts to a space that's maintained at 50 degrees Celsius. Okay, so and the outside temperature is 0 C. A minimum temperature difference of 5 degrees C is required for heat transfer in the evaporator and in the condenser. And atmospheric conditions, or the dead state conditions, are given here, and we are to determine or do a exergy inventory on a rate basis for the entire cycle, complete with an exergy flow diagram, and determine the power consumption and the net exergy efficiency and the COP of the system. And so let's just say a few things about what's been given here and what we know. Okay, it is an ideal vapor compression cycle, so that means that the evaporator is evaporating the working fluid up to a quality of 1, or a saturated vapor. So state 1 is a saturated vapor. We also know from the information that the condensation that occurs is to the saturated liquid condition, a quality equal to 0. We also, given in the problem, we know that the warm region is at 50 degrees Celsius. We know that the cold medium is the outside, which is at the dead state. As it says here, that a minimum temperature difference of 5 degrees Celsius is required for heat transfer in both of these devices. And so what that implies is that the working fluid, which is the R134A, is going through this evaporator at 5 degrees below the 0 C. And so the cold medium is 0, and the evaporator is running at a refrigerant that is at -5. And so because of that, then there is heat transfer boiling that refrigerant at -5. Likewise, since the warm region is at 50, in order for there to be heat transfer from the refrigerant to the warm region, the temperature that is in this condenser cannot drop below 55. Okay, there has to be at least 55 degrees of temperature difference for the refrigerant to transfer heat to the 50-degree temperature. So that means that this temperature here at state 3, if that's going to be the saturated liquid condition, that's going to be at a pressure that is associated with a condensation temperature that is at 55 degrees Celsius. Okay, so that's basically telling us what our two temperatures are going to be, or excuse me, our two pressures are going to be. And so this 55 degrees as a saturated liquid is going to tell us what the pressure is at 2 and 3. Obviously, as it comes out of this compressor, it's going to be at a higher temperature, but that's okay because it's going to be higher than the saturation temperature of 55. And then we also know that the expansion valve goes to a pressure, and that pressure is dictated by the temperature throughout the evaporator at -5 degrees Celsius. And so that gives us some information that we can work with. It gives us the two pressures that we're operating this system with. And so let's go ahead then and let's go into our test apps. And we are doing, in this particular case, a vapor compression heat pump. And so it is actually a heat pump. And so in this particular case, when we look, there really isn't, as you go through the process here, there really isn't a heat pump per se, but it is a vapor compression refrigeration cycle, which we know is can also be a heat pump. Okay, so again, there was no heat pump shown here. Now. There is a test app up here that we've not really looked at, and that test app is this closed steady cycle. And if I click on that and I take a look at what's there, okay, it's currently waiting. Maybe it's not available. Okay, I'm going to back out of this and I'm going to see if it's available again. It's trying to connect. I don't know if we've got, if the system itself is down. Okay, we're gonna go back. Let me just try going into the test app. Let's just go and try this particular test app and say that it's a vapor compression process. And I could launch that. Now, something is amiss, and that particular app doesn't seem to want to work. But we'll talk about that later and possibly in class. And so, what we're interested in determining is the pressure associated with state 1. Again, we know that it is a quality equal to 1 coming out of the evaporator, and we know the temperature. Okay, let's see here. Okay, again, I forgot to, okay, it seems to be locked up here a little bit. Let me go back again. And okay, we're having some issues. Okay, again, go to my test app, go to my refrigeration gas, go to my phase change compression cycle, go to my test app. I forgot before to actually select 134A, which is the working fluid. Again, my quality at state 1 is 1, and my temperature is, okay, see, it's not allowing me, for whatever reason, to select anything else. If I turn, well, see, it's not even allowing me to turn that off. And so I'm going to go back again and see if I can figure out what's going on. Here's my refrigeration to my PC, to my test app. And let's just go ahead and see if I pick 134A. And let's say that I go ahead and I put in the temperature here of -5 Celsius. Okay, it did take that. And now let's see if I select, it's not allowing me to select anything else. And so, okay, let's see, maybe it just did. Okay, so I'm going to put in my quality equal to 1. And we'll see if it communicates. It should be for R134A. Okay, it does determine for us for that particular saturation temperature and at that quality, it is determining that the pressure of the evaporator is 244. And for right now, I'm going to put in an m dot equal to 1. And we're going to scale that later in order to come up with the the heat transfer in the condenser as 20 kilowatts. And so we have our state 1, and we know that our state 1 is at the pressure that's shown here. Let's now jump over to state 3, and state 3 is the outlet of the condenser. And we know that the outlet of the condenser is at a 55 degrees Celsius, which is, it maintains that at least 5 degrees of difference in temperature between the refrigerant, which is higher in temperature than the space itself. And so it then does the calculation here and shows that the pressure in that condenser is 1491. Again, I'm going to put in an m dot equal to 1 here. And so now we have state 1 and we have state 3. Okay, we're ready now to go back to state 2, which we know is at the same pressure as state 3. Now that we've determined that, and we know that the process was an isentropic process coming from 1. And again, it also has the m dot equal to m dot 1. And so that gives us the output of the compressor. And so we see that the compressor generates a fluid that's at about 61 Celsius, and it's going to desuperheat down to 55, and then it's going to go through the condensation process where it goes to the liquid at 55. And the final state then is state 4, and state 4 is at the pressure 1 that we've already established. And what we know about state 4 is it has the same enthalpy as the saturated liquid at the exit of the condenser, and it also has an m dot equal to m dot 1. So we have all of the particular state points. If we look at the graphics panel, and the graphics panel is showing to us on the TS diagram, we have the conditions that that are necessary. If we wanted to see what this looked like on a pH diagram, we now see that there is our pH diagram, and if we allowed a constant pressure to go through state 1, we see that's the constant pressure associated with state 1, and then we can go over here and select state 3 and look at the constant pressure line through there. So again, that is our pH diagram. We can also say, let's look at a constant entropy line going through state 2 and 3. Now, something happened right there, but it still is approximately a straight line right there. And so we could also say that at state 3, we could do a constant enthalpy line. So except for this little blip here, I'm not really sure we have the 4 states given. Now let's go back then, or let's go and identify our various devices. And we'll start first of all with the compressor. The compressor goes from 1 to 2 with no heat transfer. And we see the amount of work that had to go in per 1 kilogram per second of fluid. That's our compressor. We then have our condenser, which is from 2 to 3. And again, this is where we have our heat transfer that we want to be at least 20 kilowatts. And so since there's no work being done, we see that it actually is 153.355. 153.355. And so we need to reduce the mass flow rate down by a certain amount in order to then maintain or have this show up as 20 kilowatts. And so our device 3 is just our expansion valve from 3 to 4. And we know that nothing is happening there, so 0, 0 on our work and heat transfer. And then finally, we have our state 4 to state 1, which is our evaporator. And the evaporator is, is bringing heat in from the cold environment no work being done, and we see that it's bringing in 115 units for the flow rate that we specified. Okay, so with that in mind, we're going to now go back to the state panel. So if I went back to this number here and copied that number, oops, I can't do that. Okay, I'm going to go ahead 153.355. And so now if I go back to my state panel and go to state 1, this m dot, instead of being 1, I want it to be a fractional amount. And that fractional amount will be 20 divided by 355. And so that is the m dot. And so if I now go and do a super calculate, all of the states will be recalculated with that m dot. And now if I go back to my device panel, we'll now see that the heat transfer between 2 and 3 is the 20 kilowatts that we were shooting for. And so we've got the system, we've got the states, and we have the m dot all now determined. Okay, so if we if we then went to the cycle panel, we can then look at what's presented here. And so what we see is the Q dot out of 20 is identified. The evaporator is bringing in 1507 because it also scaled, and then the amount of work that is required is this right here. There was nothing in the expansion valve, so the net work is a certain amount. And so the coefficient of performance for this heat pump is going to be this value of 20 divided by the net work. Now you'll notice that there is a cycle type up here that identifies the refrigeration cycle. Now, in this particular case, if this is selected, this is the heat transfer that's occurring at the low temperature for this amount of work. And this COP then would be this value, 15 divided by about 5, which is the 306. But what we have is a heat pump cycle. And so when you select the heat pump cycle, now if you do a super calculate and you go back to the cycle panel, now you see that this Q dot out is the 20 kilowatts. You have the same net work, but now because it's a heat pump, it's taking this value divided by this, and it's coming up with a COP of 4.06. Okay, and so the COP for the system that is being asked for in this particular problem is 406. Now you may have noticed that when we selected the refrigeration cycle that the COP was exactly 1 unit lower. It was 306. And that makes sense because the difference between the two heat transfers is always the amount of the work. And so when we have, as part of our heat transfer, we add the work of the compressor, since we're dividing by the work of the compressor, it's always that COP for a heat pump is always going to be 1 unit greater than the COP of the same system for a refrigerator. Now, the one thing we failed to do in this whole overall problem is going back to the state panel and selecting a state 1, because we do have, it is asking for exergy here, and we see that the atmospheric ex-Z state conditions are 100 and 0. And so once we put that in and do a super calculate, now we can go back and we can ask ourselves, what else did we needed to add? And so if we go to the device panels here, you'll see in the various device panels, you'll see that it actually established that the dead state temperature or any heat transfer coming in needs to be identified from what temperature. And so in order to do this properly, we need to know what the dead state temperature is. And so back here on device 1, this was the compressor, and there was no heat transfer in the compressor. This is the condenser, and the heat transfer in this particular case is 20 kilowatts coming from the warm medium, which corresponds to a temperature of 50. And so the TB for this particular case is 50 degrees Celsius. And so again, this heat transfer is actually being transferred in exergy-wise from a temperature that is the warm medium's temperature. Okay, then when we go to the the expansion valve, there's no heat transfer, so you don't have to worry about this TB. But now when we go to the device 4, which is the evaporator, we know in this particular case that the heat transfer is coming in. The heat transfer that this is bringing in from the cold medium, it's also at or coming from the dead state temperature and not 298. And so now we have those properly given. If I do a super calculate then, and it recalculates everything. Okay, recalculates everything. Okay, and now if I go to my okay, let's see if I need to, need to do any recalculation here. Something seems to be, okay, amiss. Okay, if I go to my device panels and let's look at our devices, calculate, 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 cycle panel, super calculate. Okay, so it's saying that it started and there is no changes. And so it's not going to be updating for whatever reason. And even if I hit this here, so I will determine what happened here. I think the problem is that I should have put in the dead state at the beginning of the process. And after putting in the dead state and the corresponding temperatures that the heat transfers were coming from, I believe that this would have been calculated. So I will I'll check on that and get back with you. Okay, there's been a gap here. I went back and re-looked at the problem, and the answer to the COP is 406, and that's the number that we saw. The rate of work ended up being 491 kilowatts, and that's due to the reduced amount of mass flow rate. And then also on the cycle panel, one saw that the second law, or exergy efficiency, was calculated to be 62.93. I left everything in the refrigeration cycle for whatever reason. When I switch over to the heat pump cycle, it didn't appear to want to work. I'll be looking into that and reporting back.